Hello, and in this Commodore 64 demo peek video, we are going to look at bitmap horizontal scrolling, vertical scrolling, and then bouncing a bitmap screen around. Now, bitmap screens on the Commodore 64 have 10,000 bytes each. So it's actually quite a lot of work for just the CPU to scroll a bitmap. So how does this demo horizontally scroll this bitmap screen quite quickly? So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. The graphics map debug view shows the bitmap data doesn't actually scroll in memory, and the graphics map for the sprite debug view there shows that the scrolling message is actually comprised of sprites over the top of the bitmap. The memory debug view doesn't show that much memory being copied around, so how is this screen scrolling? With apparently not much effort. Now there are some reads and writes going on here. So we have some writes going into the color RAM, we have some writes going into the screen memory, which in bitmap mode is used for extra color data. And we can see that if we look at one of the screens, which is actually used as color memory for the bitmap, we can see that it's initially being cleared with black, and then the fist shape progressively comes onto the screen. If we use the edit mode here in the graphics map and then start drawing X's, look on the left hand side there. The C64 output is actually showing that it's actually moving the screen. So the fist graphics characters, if you like, are actually just wrapping around the screen boundary. And it's just that the colors for this bitmap are being set to black. So it looks like it's a black part of the screen, and only one screen for the bitmap data is actually scrolling onto the screen, but it's not. It's actually the same bitmap data side by side for this screen layout, because the Commodore 64 is just shifting this bitmap data horizontally on the screen. Now, if you've watched one of my other videos, which was, I think, Creatures, then Creatures uses a technique called horizontal screen positioning, or DMA delay. But basically, there's some updates going into the VIC chip, which causes the VIC chip to delay when it first starts fetching character data from the video matrix. We're going to look at this in more detail in C64 Debug GUI, because we can actually look at the raster and instruction timing for this demo, and then we can understand a bit more about what this effect actually entails. So we can definitely see here that we have a sprite grid. We can see the red bounding boxes around those sprites. So the sprites don't actually move. The sprite data actually is being shifted across to the left, and the sprites look like they're in high resolution mode, so the pixel level scroll is perfectly fine even with expanded sprites. Now, using the debug targeting cursor, let's see if we can find out what is going on at the top of the screen to try and understand how this scroll is going. You can see that I've stopped it at a certain point where only half the fist, half the screen is being shown. Because this is using what I think is a DMA delay technique, or the HSP technique, it's the same one. It's just called different things because different people have called this technique different names in the past. And to be honest, one hasn't really stuck. I'm just moving the targeting cursor around in the raster line schedule so that we can see on the left hand side the instructions that are being executed at certain cycles In the video frame, I've paused the execution so that we can actually see one whole video frame here. These D392, D3A2 memory locations are actually being mapped back into the VIC chip. I have a feeling that the code is using these D3A2 locations to try and obfuscate the way it's using the VIC chip, but because of the way that the VIC chip is banked into memory, all of the memory in this lower range of D000 to D3FF are all mapped into the VIC chip in, I think it's 32-byte chunks. So the VIC chip registers are mirrored, I think, in 32-byte chunks progressively through that larger chunk of memory. It's just easier for the address decoding to work that way. So D399 corresponds to D019. So it's just doing some updates to the VIC chip registers here. I'm just looking for what I think is going to be the DMA or HSP routine. It looks like here that it is updating the jump at 1049, 104A, 104B. It looks like it's updating the jump address. The disassembly for the jump address I don't think is updated, but when we do a jump, we'll see where we jump into. It looks like it's using a lookup table to decide what routine to actually start running. There we go. Progressing through the raster line schedule. We can see it's actually updating more self-modifying code there for the JSR down at 1095 there. Looks like there's a slight little load X, dex and branch on not equal delay loop there. And there we go. We've JSR'd into a whole bunch of NOPs. Now you'll notice that those no-ops, it jumped into the middle of the no-ops, but if you jump into different parts of those no-ops, either high up or low down, you're going to be spending a different number of cycles. So what this routine is doing here is that it's storing into D391, which in the VIC chip, it corresponds to D011, which is the VIC2 screen control V. So you'll notice that if I scroll backwards just a little bit, just before this instruction is executed, the sequencer state is idle and the bad line state is no, and the row counter is 7 up there in the debug information. Step through until the instruction has done the store, then we suddenly get into the bad line state in the middle of the raster line. Now when the VIC chip is told to go into the bad line state in the middle of the raster line, this is what triggers the DMA delay technique. Basically the VIC chip starts, because it's in a bad line, the VIC chip will want to start fetching character definitions at that point. So you'll notice now that as I step through the remaining part of this raster line, through the remaining cycles, the CPU has stopped. It's not executing any more instructions because the VIC chip has stunned, it has paused the CPU at this point. And it is currently fetching extra character data. This load A with D392 corresponds to D012 in hex in the VIC chip, which is actually the raster beam position, the vertical raster beam position, not the horizontal one. So now we are in the display portion and the bad line state has been reset to no. The VIC chip will start displaying character data or bitmap data corresponding to the number of characters that it has read in for the previous bad line. Now, because the bad line condition was triggered, several cycles in or several characters into the actual raster line itself, then it has actually read fewer than 40 bytes for the current row. So the VC base for this displayed position is actually not a multiple of 40 bytes in decimal. or 2 8 bytes in hex. It's actually 1 7 bytes because it was triggering this DMA technique on the, I think it was the, well, it's triggered it some part way into the raster line, but then the remaining part of the raster line where it was a bad line read in that many number of bytes. So that's where the VC base offset comes in. The VC base offset is the offset in which it starts reading bitmap text screen data. The bitmap screen is tied to the text screen VC base. It uses that as a memory address lookup for getting the memory. Now, on the Commodore 64, every 8 lines, the VIC chip needs to access more memory to read in the character definitions that it will display for that 8 pixels character row. So that's why the CPU is stunned or paused, is that the VIC chip needs to grab memory for every single cycle, every single half cycle actually, because it accesses it twice for each cycle. Usually the VIC chip and the Commodore 64 CPU share the memory. One half of the cycle, the VIC chip accesses the memory, and then the next half of the cycle, the VIC chip, the CPU can access the memory. But when the VIC chip needs to read the extra character data, it will stun, pause the CPU for an extra 40 cycles or whatever it is for the data to get the data for the scan line. So that's why the CPU wasn't executing any instruction until after the bad line condition completes. So I'm just running through the little calculation there to do a bitwise AND of D3A7 with D01F, so that then we can get back to, there we go, and that's D007, for example. So now we know that this part of the code is updating the sprite Y position. To be honest, I don't think the scrolling text message actually updates its Y position at any point during this part of the demo, so I don't know why it continuously stores it and refreshes it, but hey ho, never mind, that's what it does. So anyway, now we have a look at the code in the C64 debug GUI VIC cycle and CPU debug code. We know for sure that it's using the DMA delay or HSP technique for delaying the fetch for the bitmap character data. These are just the ROL instructions for shifting all of the sprite data. So once the DMA delay technique has been executed, it doesn't need to keep on executing it for each row in the screen because the VC base offset has already been tweaked. We don't need to keep on tweaking it for as long as that screen is being displayed. But the same code needs to run again to retweak that VC base value to make the screen horizontally scroll. And as luck would have it, we can tweak it so that it offsets VC base by 0 bytes or by up to 39 bytes, so that we can actually scroll the entire screen horizontally from 0 to 39 bytes. So that allows us to scroll the whole screen. And basically what's on the left or right hand portion of the screen will just wrap around, and that's the way that the VIC chip renders the screen. So now let's have a look at vertical scrolling for the bitmap, because it's possible to scroll the bitmap screen vertically very quickly as well, using a different VIC chip tweak, if you like. It's actually in part of the triangle road of excess mega demo. So I'm just skipping through the screens, which I'm not interested in until we get to the interesting screen. Bear with me for a second. So here we go. This is the screen that I was interested in. Just going to save a little snapshot just in case I want to edit this later on. So this screen, you'll notice that there's a collection of sprites, I think, moving around at the top of the screen. But we have this bitmap screen underneath, and actually we can control the speed of the bitmap screen scroll, but even without controlling the speed of the bitmap screen scroll, it's scrolling quite quickly. So we can see in the debug graphics map that the sprites are in the last bank. We're not really interested in the sprites. It's what we're interested in is actually why and how this bitmap screen is rendering like this. Look, so one scroll through the screen. Look, the screen data in the memory is actually not scrolling, but it's scrolling on the Commodore 64's view, and we can see that actually it's progressively drawing the screen from top to bottom, continuously as the screen scrolls up. And we can see that the King Tut mask there was offset. If I make it scroll really quickly, you can see that it can scroll really very quickly indeed. So now the screen data in the debug view is it's not half and half, it's centered properly, but then when it scrolls to the next screen, it's offset horizontally, and the next screen is offset horizontally, and this screen is offset horizontally, and then it synchronizes back again to a properly centered screen from the point of view of the debug view. If I use the editing feature in this debug graphics map view here and fill it with some dots, you can see that the Commodore 64 is rendering these extra dots quite happily, as long as the colors aren't filled with black. Then the pixels are showing up on the Commodore 64, so we can definitely see that it's actually the bitmap screen that we're looking at on the C64 view is actually correct in terms of the memory debug view. So how is this demo scrolling the bitmap screen vertically so quickly without shifting around all of that memory for the bitmap view? It's just rendering new rows, it's not shifting the whole thing. So let's have a look. Here we are back to that screen now, but in C64 Debug GUI. We can definitely see again the sprites up at the top of the screen with some Y expansion going on as well, which is rather strange, but yeah, we can definitely see the red bounding boxes for the sprites. But what we're really interested in is having a look at this in the VicChip debugger with the cycle level debugging. And we'll move around the raster beam and then we'll see where the bad lines are. Now I've already enabled the bad lines, but it doesn't seem to be displaying the bad lines correctly in this debug view. But what we do have here, do you see that, what is it, that light bluish turquoise colour growing there? This gives us a good hint about how this bitmap screen is being scrolled vertically. We are in illegal text mode at this point in time. Illegal text mode is where, so for example, extended color mode, multicolor, and yeah, I think it's extended color mode and multicolor bits are enabled simultaneously, which is illegal. It cannot do that. So it turns off the video output circuitry, if you like, in the VIC, and it just renders black, or it renders, I think it might render the background color or something like that. But anyway, it's useful for hiding certain areas of the screen that you don't want to be displayed because the pixels are a mess, for example, or you want to hide a Y scroll split if you're doing a character screen scroll, for example. But if we have a look at the raster line debugging here, we can see that at this point in the screen, we are running certain instructions. So let's get to those certain instructions and then we can see what's going on. At this point in the raster line schedule, it is executing that jump instruction. Then it goes into these following instructions and I can see that it starts going into the interrupt here. And the code at EC85 is where the interrupt starts running the code. So we're incrementing D012, incrementing D019, loading accumulator with DD06, ANDing it with 1, branching on not equal to EC9. See, I think that's detecting whether or not the interrupt has been occurred. A certain type of interrupt has occurred. And then the interrupt flag is cleared after that. And then we go into what looks like a no-op slide. These no-ops just basically waste 2 cycles each until the real-time interrupt or raster interrupt comes along, and then it hops into the real code. Now, we know then that the real code has started executing at a more accurate cycle period, because all it's doing is that it's running no ops. It's not running a music routine, it's not running graphics updates or anything like that. So the way that this interrupt then starts running the load accumulator, the store, is accurate to 2 cycles. It's a useful technique for stabilizing your raster interrupt, so that you are definitely guaranteed to be running the code that you want at the correct cycle. So this starts off by storing into D015 and then storing into D017. The sprites you can see here now are Y expanded. It's running some no ops just to waste a little bit more time. It is then loading X and then storing X into D011 there. So depending on the value in the 0 page memory there, it's just doing a different branch on not equal. But basically now it's started doing that D011 store at that particular cycle in the raster line schedule there. Now this store to D011 with F5, when it's done at that particular, I think when it's done at that particular cycle in the raster line schedule, what it does is that it tells the VIC to start fetching a new bad line. It sets the VIC into a new bad line state right at the end of when it's just finished rendering the previous line. So the VIC is being told to start fetching a new line. Again, please, just forcing it to start fetching a new line. We'll just debug this raster line schedule a little bit more by hopping through the cycles and noting down what registers, especially D011, which is the VIC vertical screen scroll register. So there we go, it's doing a DEC D016, and then it's doing a store A with D011 again at that particular cycle position, and there we go, it's gone into the bad line state this time at that particular point. So it's not a bad line, and now it's done the store and it's saying I want to go into a bad line state at exactly that point when it has finished, and there we go, it's changed. So this tells the VIC chip to start fetching another character screen row or a bitmap screen row, and each row is 8 pixels high. So the VIC chip then starts saying, well, I want to start displaying a new row of characters, so I better do my job of updating the VC base pointer there. So even after just processing 1 pixel high raster line, the VIC is being tricked into thinking that it should update the VC base pointer by 28 in hex, which is 40 in decimal. So basically for 1 pixel horizontal row, the VIC has just thought that it should update, or it should have rendered 1 whole character row already, so it's fetching the next character row, or rather it's updating the pointer or the offset for the next character row. And it's done it again at the end of the line at that particular cycle. So at that particular cycle position in the raster line, it basically adds on 28 in hex, which is 40 in decimal, for each row that we want to consume or we want to update the offset. So basically, by updating the offset for a whole character row, we're telling the VIC to discard entire character rows and then fetch the next one in the video matrix. So the VC base is continuously being forced down the screen much quicker than before. So that's how the Commodore 64 and the VIC chip in particular can be tricked into scrolling the bitmap screen much quicker than normal. Now this technique is called various different things, but I've seen it most often called a line crunch. I think that's a very apt name because basically you are tricking the VIC into crunching an entire 8 pixel high character row into 1 pixel high raster line. So you're crunching the lines out of the screen. Now, because the VIC chip will, as long as you let it, render the entire screen from when you stop doing this line crunch, then this basically means that the VC base internal pointer will wrap around in its kilobyte memory space. Now, a kilobyte for the VC base memory pages, if you like, is 1024 bytes, and that is not exactly divisible by 40 in decimal, or 0400 in hex is not exactly divisible by 28 in hex. So that's why you get this effect where the VIC chip cycles around this memory block, but the screen gets offset horizontally, and then it comes back again, then it gets offset horizontally, and then it comes back again. If we quickly have a look at a default Commodore 64 screen, how the VIC chip updates VC base, how the VIC chip updates its bad line state is that you can see the bad lines being rendered there because I've switched on the bad line mode in the debugger. But we can see that the VC base pointer is updated at the end of each 8 pixel high character row appropriately. So VC base is 0 at this particular point, and the VIC is in a bad line state, and then at the end of the bad line, VIC goes out of the bad line state. It then renders the 8 raster lines, so the 8 pixel high characters, and then we get the next bad line state, and VC base is updated with 28, so now 28 is 40 in decimal, that's 28 in hex, so that now we know that the VC base graphics data pointer has been updated to 40 for the next character row, the next 8x8 pixel high character row there, the default screen. So this demo effect was just basically compressing or line crunching the entire line. Now, this next demo effect is really interesting because it combines both the horizontal HSP or DMA delay technique and also the vertical, which is the line crunch. So I'm just skipping forward to the interesting part of the demo here. There we go, a nice, I think, what is it, a Bones logo with some nice multiplexed sprites over the top. But we can see that the screen, the bitmap screen that we can see in the graphics map debug view there, is swinging around merrily, swinging around really very quickly. And there's only really one way that you can do this on a default unexpanded Commodore 64, and that's to use the HSP and DMA delay technique and the vertical line crunching technique. Now we can see in the text screen view there, which in bitmap view, remember, that is actually one of the color screens. We can see the color screen data is being read in two separate banks there in the debug memory view. And we can see that using the bitmap debug view there, that we could see two separate parts of data chunks in memory that were being read and then copied into the two different color screens there, one in the color RAM and then one in the color screen data. So I've just saved a snapshot there so that we can use the debug graphics views again to futz around with the memory so that we can try and understand what this routine is doing a little bit better. So first of all, I can see that the dark areas of the screen, the black areas of the screen, are actually being cleared with @. It's a similar effect to the horizontally scrolling FIS or IK Plus logo, where we didn't want to see, or where the demo didn't want to see the screen data wrapped around, it was just blanking it out with black characters. But if we start filling in the pixels for the bitmap screen, we can definitely see what's going on in the Commodore 64 view. We can see that we're actually rendering a lot more pixels in the bitmap view. Now this blank area of memory here is just blank. We're just filling it with some pixels, but it's not going to render above the standard bitmap size for the Bones logo. What we really want to do is that we really want to stop the screen being filled with black characters. So I'm just editing what looks like the color screen data, and you can immediately see there on the left that we start getting the repeated bitmap data for the Bones logo. So I'm just going to fill in as best as possible with this debug editing stuff here. I'm just going to fill in all of these black pixel gaps here, which is color RAM data, okay, and then we can start seeing actually that the Bones logo is now being surrounded with differently colored Bones logo bitmap data, and that's because the values that I'm putting into the color RAM copies there are, they don't correspond to the actual pixels in the logo. So, but we can see here that the demo is actually shifting around the entire screen, and the screen is tiled horizontally and also vertically, of course, because that's the way that the VIC chip just renders the bitmap graphics data. It just tiles, it kind of like loops around, right? So it's just tiling the entire video matrix. So actually, it looks a little bit more impressive, doesn't it? If you know that you're actually swinging the whole tiled screen around. So let's fill what are the last 8 characters of the bitmap data, okay, with what is it, AA, which is 10101010 in binary. And there we go. Because we're running the multiplexed sprites over the top, the multiplexer needs to update the sprite pointers. And we can see now that we've put some solid color in to the bitmap data there, we can see that the screen color data, also don't forget that the sprite image pointers are in the last 8 bytes of the text screen, which is the color screen data in this case, or one copy of the color screen data. So when the multiplexer updates those sprite image pointers, we now get to see them in the bitmap. So basically the logo has been constructed in such a way that it has black screen area at the point where the sprite pointers are, so we don't see that on the screen in the demo itself. Now when I filled that whole memory for the one of the color screen backups there, I filled the whole memory with a repeating pattern. We can see now that the demo is swinging around the entire screen. So doesn't that kind of look, if you had the right colors, you would have a nicely tiled Bones logo swinging around the screen, and one Bones logo is offset with the other Bones logo, and I think, I think that would look a little bit more impressive rather than doing all of the extra effort in clearing to black the areas around the Bones logo to avoid that tiling effect being visible. I think the demo could have used both, to be honest. It could have had initially tiled and then done all the extra work to not make it tiled and to blank out with black the border areas around the logo. I think that would have been a little bit more impressive, to be honest. But hey ho, there we go. And maybe alternate between both of those modes to kind of like really drive home the fact that you are swinging around the entire screen. That would be really quite cool, right? So let's just double check that this demo is doing what we think. In other words, combining the HSP DMA delay technique with the line crunch technique. Now, I've called this combined technique of using both the horizontal and vertical techniques together. I've seen it called various different things. I've seen it called VSP for variable screen position. I've seen it called AGSP for any given screen position. So I don't think, it depends on who you ask, and it depends on where you see it being documented. But there we go. We're debugging the raster beam sprite, the raster beam cycle schedule for the VIC chip, and there we go. We've got another no-op slide, and it looks like it's doing the line crunch first. So it looks like we're doing a line crunch. Let's just keep on going through the cycles. Look for the bad line state. We're currently in the idle state. Look for the bad line. Look for the VC base being updated. There we go. It's just doing a little bit of raster beam synchronization there. So the sprite scrolling message up at the top of the screen is reusing this blank area of memory where we're doing the line crunches. So we're looking for the bad line state progressing. We'll just keep on going through the cycles. VC base is still at 0 currently. So there we go. We'll keep on going through. It's doing a store into D011, which basically tells the VIC that we're right at the end of the line. We're now in a bad line state. We've basically told the VIC that we want to crunch the line by tweaking the value. And there we go. VC base is updated to 28. It's now updated to 50. So yes, this demo is doing a line crunch first. We keep on going through the cycles. It's still doing that line crunch code. Eventually it gets to this position here. Now we must really start seeing the DMA technique come along to kill the VC base, or to tweak it rather, and there we go, it's happened just right there. So it went from 230 to 232 around about this time. Just narrowing down the targeting cursor for the correct cycle at which it's done that. So 232 is obviously not aligned with 28 in hex, obviously, so it's read an extra few characters, so it's offset the VC base, the character base offset appropriately for the horizontal position that it wants to move this bitmap screen. And now it's rendering the sprites, it's rendering the screen. Interesting to note that the C64 debug GUI graphics view there is actually showing the bad lines, as opposed to the previous demo that wasn't showing bad lines for the vertically scrolling screens, so that we can see the schedule. There we go. There's the deck D011. There's the increment D011, and it's doing it right at, or almost at the end of the character screen there. So basically it's telling the VIC that it wants to go into a bad line state at that position there. So for the last few cycles of that raster line there, it goes into a bad line state, which basically gets the VIC to fetch a couple of extra characters at that position. So if we put a breakpoint now at that instruction, which is the DMA HSP trigger instruction, we can see that this dec and increment of the D011 register is actually appearing at different raster X positions. As each frame is advanced, watch the raster X red, and we can see that it's raster X at 140, 138, 128, 120, 118. The reason why it's going in 8 pixel jumps is just because each cycle is 8 pixels wide. Each CPU cycle, 1 megahertz CPU cycle approximately, is 8 pixels wide. And that just basically tells the VIC chip to fetch a variable different number of horizontal characters to finish off that last character line row by telling the VIC to do that bad line state for X number of characters and pulling in that new number of bytes into the VC base and just updating the offset that way. So this demo cleverly does the line crunch first and then does the DMA delay. Basically, a few lines down, a few character rows down from where the logo needs to start being displayed. And then basically, I think it's probably using the same technique of using the illegal text mode, probably, to mask out the area up at the top of the screen. That's the simplest, cleanest way of doing it, like the other demo was. And then basically turning on the screen and turning on the display, and then the VIC chip will render the bitmap screen at its particular offset. So we've got some code to do this. I'm going to provide some example code to show how to put all of these techniques together. Let's just get the editor up and running. Let's just enable the HSP DMA delay example first. And if I move the joystick left and right, then you can see here that the screen is being scrolled left and right, but it's only being scrolled by this stable raster interrupt here, doing the DMA register tweak, DMA delay register tweak on the VIC. If I enable the line crunch, then moving the joystick up and down will progressively add 1 line of line crunch depending on how far up and down I move the joystick. So there we go, we can see that we can move up and down in character row steps very quickly just by doing a line crunch. The little red bar, green bar there indicates exactly how much line crunch I'm introducing. Now, text screen, bitmap screen, doesn't really matter. The VIC chip uses that VC base offset to fetch bitmap data. And you can see here the horizontal screen position is being done before the line crunch, as opposed to the line crunch and then the DMA delay technique here. But I just did it that way because I didn't really want to change the code that much. I just had the DMA delay done in the top part of the border just before it starts displaying characters, because it's just an easier place to do it. So you can switch on the debug view, and that means that the illegal text mode is not being enabled. So you can see all of the lines up at the top of the screen being crunched. Now, every time a character row in the screen is being crunched, you get this, basically in this case, it's a black line. It can change depending on if you've got bitmap mode enabled, I think, and this is just text screen mode, so you just see a black line. It's just repeating, I think, the last row of pixels. And I think because the character set has a black bottom row, then I think that's just basically what's being displayed, I think. Anyway, but so basically the screen, the line crunch is displaying as this black area, And that means that the bottom of the green bar there, the bottom of the red-green raster effect bar, that's where the screen should have been turned back on again, but the screen just hasn't been disabled using the illegal display mode. So you can see all of the rubbish that you don't really want to see. So that's why these demos, they tend to cover it over with sprites. They tend to use the illegal text mode to turn off the graphics sequencer, so that basically you just don't see all of this rubbish and you see a nice clean effect. You can see here the character rows, the character screen is showing that nice little offset between the tiled screens. The same character rows, just I can move around with the diagonals and I can scroll the text screen around very quickly. Same as that bouncing logo swing. So all of this code is in my public C64 public GitHub repository. It is this raster test2.a source file, and you can just get it all from there. There is a little build it batch file which calls my heavily tweaked version of the Acme assembler, which will then output a PRG, which then you can just run in the emulator or on a real Commodore 64. There's also a link I'm going to put in the video description to the codebase article on AGSP, which is the any given screen position, or variable screen position, however you want to call it. So thank you very much for watching these Commodore 64 demo peek videos. If you like this kind of deep technical dive into VIC hardware tricks, or I might actually go into some SID tricks as well for demos. If you like this kind of stuff anyway, then please do consider liking or subscribing to this channel, and I really hope to catch you around next time. Have a great day, or evening, or night, wherever you are.